Hey guys, in this video we're going to be going through the Pix2Pix architecture for image translation. In the last video we went through generative adversarial networks or GANs. I showed you how they work, the loss function, how to train them, and I also weighed up their pros and cons. In this video we're going to take the GAN a step up and we're going to use the GAN to translate images. But before we get into that, let's just quickly recap what a GAN is. A generative adversarial network's objective is to generate images. So I can give it a collection of images, like let's say a collection of faces. I can feed it into this GAN, and by the end of training, the GAN will learn how to generate new faces. And these faces will be completely new faces that weren't in the original training set. And that's why these generative models are super cool. So in generative adversarial networks, we actually have two neural networks, a generator and a discriminator. And these two networks have opposing objectives. So they're actually competing against each other. The discriminator is aiming to distinguish between real and fake images, or another word for fake is generated, so real and generated images, while the generator aims to generate images which fool the discriminator. So they kind of compete together and they battle it out. And by the end of training, we want the generator to be able to generate images that look so similar to the training set that the discriminator isn't able to distinguish between the real images and the generated images. And that's how we know that the generator has won. Okay, so that should have been recap. If you haven't watched the last video on generative adversarial networks, I highly recommend you watch that because we're going to use a lot of those concepts as foundational knowledge for the content in this video. So if you haven't watched that, please go check it out. It's a great video. It explains everything you need to know about generative adversarial networks. I'll put the link in the description. And just for further recap, I also have a diagram of the generator, discriminator, or GAN architecture. And we're actually going to modify this for the Pix2Pix architecture. But this is just a simple GAN. So we feed in some noise to the generator, we get a generated image, and then we feed that generated image into this discriminator. The discriminator is going to tell us if this generated image is real or not. So it's going to output a probability. It will output 1 if it believes that the generated image is real, and it will output 0 if it believes that the generated image is fake. Now, at the same time, we're going to be passing images from the training set to the discriminator, and it's going to be also determining if those are real or fake. So that's the GAN, and that was a recap of the GAN. But let's actually go to the Pix2Pix architecture. So what is actually the Pix2Pix architecture? So in regular GANs, we would input noise into the generator and we would get a generated image. But in something called conditional GANs, we're actually inputting into the generator a image, so an actual image, and this is called a source image. And what we're doing is we're passing the source image through this generator, and that will output a generated image. Now, the source image and the generated image are of the same shape. So you might be asking, what's the use of this? What's the point of passing an image through a generator and then getting another image out the other side? Well, it seems that this is actually useful for something called image translation. What's image translation? Image to image translation is when we take an image from one domain and transform it into another domain. I have some really good examples from the original Pix2Pix paper, which I think really do a good job of explaining what image to image translation is. So we have a bunch of examples here. In this first example, we're translating labels to streets. So you can see this input image is a semantic segmentation of a road. And then what they did was they trained a conditional GAN to take in this image and output a realistic looking view of a street. So the generator can take in this image of labels and it can generate this realistic looking view of the street. In another example, we can take this labeled of a facade, of a building facade, and it will output the actual realistic facade. Another example is converting black and white images to color images, or aerial images to maps, or day images to night, and or edges to photos. And there are so many more applications. You could build a generator, a conditional GAN that translates summer pictures to winter pictures, and that could be pretty cool. So that's what image to image translation is. And I think now you can see why this conditional GAN might be useful. So we're taking in this source image, which is, and for the entirety of this lesson, we're going to be using this edges to photo example. So in our conditional GAN example, we're going to be inputting this image of edges. So that's going to be our source image. Then the generator is going to generate the image of the actual handbag. So the edge to the handbag, so this is the source image, and this is the target image. And the generator is going to be trained to translate this, the edges, to this, the actual realistic looking photo. So it's sort of image generation in the sense that we are generating new pixels. So we're translating an image from one domain into another. That's what image to image translation is. And that's what conditional GANs can help us do. Now, there are multiple conditional GAN architectures of ways of doing this, but Pix2Pix is the one that we're going to be going into this video. So let's actually now understand what the Pix2Pix architecture looks like and how this is actually trained. Okay, so first up, what does our training set look like? Well, in this example for conditional generative adversarial networks, we actually have labels, and we actually have image pairs. So the first image X is the image from domain A, and the image Y is the image from domain B. So we're trying to build a GAN that can translate images from domain A to domain B. And this is actually supervised learning, right? Because we have labels. We have a feature, which is our source image, and we have a label, which is our target image. So we do need a paired data set to make this work, to make this Pix2Pix architecture work. In a regular GAN, we didn't need labels. We just needed a collection of images. But to build this Pix2Pix architecture for image-to-image translation, we actually do need these XY pairs. Okay, let's get into a little bit of notation before we actually get into the architecture. So X is our source image. Y, so you can think of X as the picture of edges, the handbag edges. And Y is our target image, which is the realistic looking image of the handbag. G of X is our generated image. So in a regular GAN, this would have been G of Z, right? Where we're inputting the noise into the generator. But now we're actually inputting the source image into the generator. So so we say it's G of X, and that's the generated image. And now we get to the discriminator. So the discriminator outputs the probability that a certain XY pair is real. So d of x of y, d of x comma y is equal to the probability that a real image is deemed real. And similarly, we can input the pair x comma g of x. This should be g of x. And this is the probability that a generated image is real. So you can see that in a regular GAN, we would have only given the discriminator this y value or this g of x value. But in this conditional generative adversarial network, we're actually going to be giving the source image as well as the target image. So the target image could be the actual target image, so the ground truth handbag, or it could be the generated image by the generator, which is what the generator thinks the realistic handbag should look like. Okay, that was a lot. That was a lot of words. I think it will be really useful if we go through a diagram and actually understand how this works. So this is the Pix2Pix architecture in a nutshell. We have a source image, and we're going to be passing it through this generator. Now, just a quick note on what this generator actually looks like. So in the last video, in a regular GAN, the generator would just be a convolutional neural network, right? it will be taking the noise and upsampling it into an image. In this case, the source image or the input and the generated image, the output, are the same shape. So we're actually going to be downsampling the source image first and then upsampling it into the generated image. And this architecture is called the UNet architecture. Now, we're not going to go into the specifics of the UNet architecture in this video, but I provided the links in the description box below so you can learn more about this architecture. It's essentially an encoder decoder with skip connections added. But all we need to know for this example is that it takes the source image and transforms it into a generated image. All right. So we take the source image, input it into the generator, get a generated image, and then we pass x and g of x into our discriminator. And the discriminator outputs this value, d of x comma g of x, which is the probability that this x g of x pair is real. Now, at the same time, we also have a target image, right? We have an image of what the translation should actually look like. So we're also going to be passing that into the discriminator, and we're going to be passing in the xy pair, and we'll also get a probability that that is real, that pair is real. I know this diagram is kind of vague and it's kind of hard to understand with all the symbols. So I actually got an actual example, and I think this will make it really clear. Okay, so we have our source image X. Remember, the problem we're trying to solve is we're trying to create a model which can translate a photo of edges into an actual photo. So we can get this edges of a handbag and it will generate a image of the actual handbag, the realistic handbag. So we can see our three images here. We have the source image X, which we pass into the generator, and that gives us our generated image, G of X. And we also have the ground truth, the target. And this is part of our training set. We have those XY pairs, and this is the ground truth, what the generator should actually output. So we pass this X and G of X into the discriminator. So that's these two images right here. And we get probability. So this is, the discriminator is trying to find out, okay, is this actually a real XY pair? Is this valid? And it will output a probability whether that pair is valid. And similarly, we also input the ground truth into the discriminator so the discriminator can actually learn what real pairs look like. So we input that pair, so this is the XY pair from the training set, and we also get a probability that the discriminator, that pair is real. So I hope that made sense. If that didn't make sense, just keep looking at this diagram, work through the logic, and I'm sure you'll get it. But I think what will actually help it make it click is this diagram over here. All right. So what we want to be asking ourselves is, what does an ideal world for the discriminator look like? So in discriminator heaven, where the discriminator wins the competition, what does that world look like for the discriminator? And what does that world look like for the generator? What does the generator want to happen in the case that it wins? So for a discriminator, given an X and a generated image, the discriminator wants to output 0 for that pair. And given an actual pair from the training set, the discriminator wants to output 1. This is an ideal world for the discriminator. In this case, the discriminator is able to accurately distinguish between real pairs and fake pairs. Okay, what does an ideal world for a generator look like? For the generator, given an X and G of X pair, it wants the discriminator to believe that that pair is real. So it wants the discriminator to output 1. And that's an ideal world for the generator. Now, of course, in the end, we want the generator to win. And that's how we actually get this good image-to-image translation model, where the generator wins. And if you train this up correctly, if you train these two models at the same pace, you eventually get to a point where the generator is able to generate or translate the source image into a target image. And that target image looks so realistic that the discriminator isn't able to distinguish whether it's real or generated. And that's how you know that the generator's won. Let's actually go on to the loss function and let's get into the details of how this network, how this architecture is trained. Oh, and by the way, you might be thinking why it's called the Pix2Pix architecture. That's because if you think about it, in image to image translation, let me go back to the examples here and I think it'll make sense. In image to image translation, we're essentially taking each pixel and mapping it to a different pixel. So it's kind of like pixel to pixel mapping, which is why it's called Pix2Pix architecture. Okay, let's get into the loss function now for this network. So, as is common with generative adversarial networks, we have an adversarial loss. And this adversarial loss is here because the generator and the discriminator have opposing objectives. If you remember this, these two objectives are exactly opposite. So, these two networks are trying to optimize for exactly the opposite objective. So, that's what this adversarial loss is. So, the generator and discriminator compete. The generator aims to fool the discriminator, and the discriminator aims to expertly distinguish between real and fake pairs. Now, this loss formula should be familiar to you if you watched the previous video, but we're still going to go through it just in case you need a refresher. So, this is the loss function for the adversarial loss. Now, log of d of x of y is the log probability that the xy pair is real. And the discriminator wants to maximize this. It wants to maximize the probability that real xy pairs are deemed real. Okay, what is log of 1 minus d of x comma g of x? Well, d of x comma g of x is the probability that that pair is real. So 1 minus that is the probability that that is fake. And we just take the log of that. So this value is the log probability that x comma g of x pair is fake. If you think about this, the discriminator wants to maximize this. It wants to maximize its own belief that this pair is fake. On the other hand, the generator wants to minimize this. It wants the discriminator to believe that this pair is real, so it would want to minimize this value. And this is where those opposing objectives come into play. And that's the adversarial loss. But the Pix2Pix architecture also mentions another loss, which is a structural loss, or you can think of it as a structural loss. Now, what is this structural loss? Well, this ensures that the generated images resemble the input image. And you can see the formula here. It's just the mean absolute error between the ground truth and the target image. And if you think about this loss, it's actually really intuitive. We would want the generated images to resemble the ground truth. And if we actually go back to the example, what this structural loss is really saying is that we want this image to look like this image. And that's a really intuitive objective. That is something that we would want to optimize for. And another really good reason to have this loss in the objective is to tackle what's called mode collapse. If you watch the previous video, you would have an understanding of what mode collapse is. It's where a generative model outputs the same image every time. So in a generative model that suffers from mode collapse, no matter what source image we would give it, it would always output the same handbag image. And that's really bad because it's not actually translating these two images. So the structural loss ensures that the generated image looks similar to the target image, and that indirectly ensures that the generator isn't just outputting the same handbag each time. Because if it was outputting the same handbag each time, then these two would have a very large difference, and that would mean the network has a very large loss. Okay, so that's the structural loss. Now, the objective for this entire architecture is summarized here. So we have a min-max optimization problem, and what we do is we have the adversarial loss, which is this LCGAN, and we also have this structural loss, which is this L1 loss. L1 loss is just the mean absolute error. And the generator, or G, is trying to minimize this loss, while the discriminator is trying to maximize this loss. And that is the objective of the Pix2Pix architecture. Let's actually see how we train this. Okay, So what we do is we pick an XY pair. So for this example, we're picking this pair, this edge to handbag pair. Let's see how we would train this. So we would input the source image into the generator, get a generated image, and we also have a target image. We're inputting these three images into our discriminator. And what we're going to do is we're going to calculate some values, which we're going to use to update the weights of the generator and the discriminator. So we have this first component here, this log of 1 minus d of x minus g of x. That's our adversarial loss for the generator. And we also have our structural loss here, which is just the mean absolute error, or the L1 loss, between the ground truth image and the generated image. And using that, we're going to minimize that and we're going to update the generator. Now, for the discriminator, it might be confusing why we're actually trying to minimize this value when the loss was formulated as a maximization problem for the discriminator. But when we're actually training these neural networks, we want to minimize a function. So we just need to do a bit of reframing so that we can use this value to minimize it and update the discriminator. But it still makes a lot of sense. So we have log of d of x comma g of x. This is the probability that a fake generated pair is deemed real, and the discriminator would want to minimize that. And here we have another part of the adversarial loss, which is 1 minus d of x comma y. So d of x comma y would be the probability that this xy pair is real. 1 minus that would be the probability that is fake. And the discriminator would want to minimize that for those real pairs. So these gray arrows correspond to updating the weights. So we would use this loss value to update the discriminator weights, and we would use this loss value to update the generator weights. And that's the training process done. So that was one XY pair, and we would do this for each XY pair in our dataset, or for each batch in our dataset if we were batching our dataset. So after training, we then get a generator which is capable of taking a photo of handbag edges and translating that to an actual image of a handbag. So I have some examples here of a trained generator for this task, or a trained conditional GAN. And you can see that it's given this input of edges, and this is the output which the generator generated, and this is the ground truth. And you can see that these generations are actually pretty good. I mean, if you think about it, just given this edge, the fact that these edges, the fact that the generator is able to fill that in and translate that into an actual handbag is actually pretty powerful and pretty interesting. And that is essentially the Pix2Pix architecture done. The Pix2Pix architecture is able to, translate a image from one domain into another domain. And you can think about so many use cases for this. Maybe you can translate horses to zebras, or summer landscapes to winter landscapes. There are so many possible use cases you can think for this. Yeah, that's basically it for this Pix2Pix architecture. As for the next steps, I would highly recommend going to a couple of links. So TensorFlow has this great tutorial on building a Pix2Pix architecture from scratch. So this is the tutorial. In this tutorial, I believe you do these labels to building facades, but you can easily implement this. You can easily adapt this to make a different to solve a different translation task. So I would highly recommend following that tutorial. Also, what I would highly recommend is reading the paper yourself. So reading the Pix2Pix paper will give you more insight into how they developed this architecture. So this is the Pix2Pix paper here, image to image translation with conditional adversarial networks. So just go to this link, which I'll put in the description box below. Hit download PDF, and you'll be able to read this. I highly recommend going through this. And there's actually something I didn't cover that they cover in the article, which is called the patch GAN discriminator. It's just a small modification on the discriminator, So if you want to know more about that, then please go ahead and read the paper. Also, if you want to know more about the UNet architecture, I'll put this link in the description box below. This is the article right here, so I'd highly recommend reading this if you want to know more about the UNet architecture. All right, that is essentially a wrap for this video. In this video, we learned about the Pix2Pix architecture for image-to-image translation, and in the next video, we're going to stay in the topic of image-to-image translation, but we're going to go to a different model, which is called the cycle GAN model. And this is really interesting. This is really powerful, and it's kind of an upgrade of the Pix2Pix architecture. So really excited for that video. If you want to stay tuned for that video, subscribe, hit the notification bell so you get updated. And if you like the video, send us a like. And yeah, that's it for this video. Later.